This is lesson 6.2 on definite integrals. So now we are looking at area under the curve using approximation of Riemann sum. A Riemann sum is a series of rectangles that will fit under the curve to help you approximate the area. Okay. So before we have these rectangles, we have the height and we have the width. And we're able to use uniform width for these rectangles. So now we're given the option of maybe changing the width of our rectangle so that it could be various sizes and width so that it will fit under the curve perfectly and we can have a good approximation. Knowing what we know, approximation is never ideal. However, there are cases where we must use approximations. For example, if we're given a data table and we only have data points, then it is best to have these approximations because you don't have a function to map out what you are given. So when you're given a function, it actually is better to use a function and use calculus. We're going to go over in the next lesson. But if not, then approximation is your next best bet. Okay, so here we have these things called LRAM, RM, MRAM. So what are these? Well, the RAMs, RAM, is a rectangle approximation method. So R means the right, L means left, and M means midpoint. So right rectangle approximation method, left rectangle approximation method, and midpoint rectangle approximation method. What this is doing is it's going to help you use these rectangles and different endpoints to help you approximate the area. So first thing we want to do is draw this graph. Now, I know some of your graphs may be a little bit different than mine. Don't worry about it. It still works beautifully. So here's your x-axis, right? Your function starts up here at 8 minus 1/2 x squared. So you have your 1/2, you have your 2, 2, 3, 4, 4.5 right here. And then at 5, you have negative 25 over 2, so negative 25 over 2 plus 8, negative 4.5, negative 25 right around here, and then negative 10 at the very end here. Okay, so your graph looks something like this. Okay. And you want the area that is trapped between the curve and the x-axis. So here's your x-axis nicely here. And then you're given an interval 1 to 6. So you start at 1 and you end at 6. So what you're looking at is this is the area that is trapped under all three circumstances: your interval, your function, and the x-axis. So notice now you have areas above the x-axis and there's areas below the x-axis. Area above the x-axis is a positive area. Area below the x-axis is a negative area. Okay? All right, so how do we use endpoints to help? So we're going to use 5 rectangles. So n equals 5. 5 rectangles. Make this a little bit easier. If we want, we can make it even smaller, but it's just to make our math a little bit more to work with. Okay? All right, start with RAM. RAM means you're using the right endpoints. So when you're looking at this, your first rectangle is here between 1 and 2. Between 1 and 2, 2 is your right endpoint. So you go up on the right-hand side, and you go towards the left and draw your first rectangle. That's your first RAM. Second RAM is right here. Third RAM is actually flat because the right endpoint here has nothing. And then the next one actually becomes negative. And then same thing with the last one, it becomes negative as well. So these will be your RAM. Okay? So those are your approximation. Notice some are completely inscribed and some are completely circumscribed. So we are no longer bounded by inscribed or circumscribed. We're actually having a mix of them when we're working on problems like this. Okay, I'm gonna have to erase this on my picture because I'm gonna have to use this same picture to describe LRAM and MRAM. So it's best to clean this up a bit for me. Okay. All right. So now, how am I going to figure this out? We're going to write a t-table starting with the endpoint 1. And since I have 5 rectangles, then our width is increment of 1. So 2, 3, 4, 5, 6. So you plug these into your function here, you'll get your value here. So if you plug 1 in there, you get 8 minus 1/2, which gives me 15 over 2. Plug in a 2, 2 squared is 4, 1/2 is 2, so 8 minus 2 is 6. Plug in a 3, that's 9 over 2. 16 minus 9 is 7 over 2. Minus 4 is 0. 25. 16 minus 25 is negative 9 over 2 and negative 10. Okay, so your RM has a width of 1. Everybody has a uniform width of 1, and you're going to add up your endpoints. This one started on the right-hand side, so we're not going to use the first one here. We're going to use the second one, right, because it's the right endpoint there. So we'll start with the second one. So you get 6 plus 7 over 2 plus 0 plus negative 9 over 2 plus negative 10, and you'll get a final answer of some approximation. Not very important here. LRAM, on the other hand, will use same width of 1, but now I'm going to use the right-hand side. So if I were to draw this, you see how I'm on the left-hand side. Sorry, left-hand side, and go towards the right and draw my rectangle. My rectangle is going to be completely opposite of the other one, and this one's going to have nothing because my left end here is a 0, and then the last one here will be a completely inside rectangle. Right? So that will be what my LRAM will look like. Okay, so my LRAM starts with 15 over 2 plus 6 plus 7 over 2 plus 0 plus negative 9 over 2, and again equaling an approximation. Okay, so the key point is to remember that RAM will not use the first Y value, and LRAM will not use the last Y value. So maybe that will help you remember. L with L, LRAM not using the last. R with R, RAM not using the first. Okay. What about MRAM? Well, if you're doing MRAM, then you need to make a new t-table. X, Y, and you plug in between points 3 over 2, 5 over 2, 7 over 2, 9 over 2, 11 over 2. Find your Y values, and your MRAM still has the same width. So you still have the width of 1, and then now these Y values that you get from this new t-table, add them up, and you'll get your approximation. So that's how you do RAM, LRAM, and MRAM, and we will always tell you how many rectangles you need to deal with. Okay, all right. Now we talked about the integral being an antiderivative. There's another way to read the integral. Another way to read the integral is when you have a definite integral. You have an a and b that stops it. Another way to read it is to see this as an area under the curve. Between x-axis and curve. And notice I use curve pretty loosely because sometimes our curve is a straight line, right? But it's between the function and the curve. Okay? So what we had before was this summation of adding up all the rectangles with various widths and various heights, and you're adding up all the base times the height, right? With the partitions getting as close to 0 as possible, right? But now that's too much to do, so it's a little bit easier to write a different notation, which is the function is f of x, and then you're trapping it between a and b. Okay, so if we take a look at this problem here, here's my equation. My equation is y equals 1/2 x plus 3. I'm going to graph it out. It's 3, up 1, right 2, up 1, right 2, down 1, left 2, down 1, left 2. Here's my line, draw my equation. Right. And then she says there is the x-axis that bounds my equation. And lastly, my interval. My interval is at -2, and it ends at 4. So very nicely, I see that I have an equation that bounds this area here, and this is a trapezoid. If it's hard for you to see a trapezoid, you may need to turn it around, because this is your trapezoid, right? The parallel sides are your bases, base 1 and base 2, and your height is right here. Area for a trapezoid is 1/2 base 1 plus base 2 times height. So in our case then, we're going to say in this case, this is 1/2, base 1 is 2, base 2 is here, that's 5, times the height, that's the difference between these two, so that's 6. So that would be 1/2 times 7 times 6, which gives me an area of 21 square units. What about something like this? Well, something like this, you need to use a little geometry. Most students don't recognize this. This is y equals square root 16 minus x squared. If you were to manipulate this function, you get y squared equals 16 minus x squared, which is x squared plus y squared equals 16, which reminds you, hopefully, of a circle. But because this is a positive square root, it's only the top half of the circle. So this one, it's really a circle, and I'm going to cheat a bit to use my capability to draw a nice circle here to show you a semicircle. Okay. And I'm going to get rid of the bottom half that I don't need. Okay. All right. So this is what it looks like. And since I'm going from -4 to +4, I'm looking at this semicircle here. So please watch out for your interval, because if your interval changes, your area is going to change. So now we use our geometry and say, hey, this is 1/2 pi r squared. So this area is really just 8 pi. Okay. All right. We're now going to venture into something more arbitrary, something more make-up, right? So we're saying that, okay, here's a tool for you. It may not make a lot of sense why you need it now, but it will come later when you need it, right? If you ever need to change your interval from A to B, we start from the bottom. The bottom is always where we start, and where we stop is on the top. If you ever need to switch those numbers, you can switch them by adding a negative at the front. Okay. Another good reminder is if you have your interval going from A to A, you don't have an interval. You don't have a region you're looking over. Therefore, your area is 0. That should make sense. Okay, a few more things. If you have a coefficient, you have a number, you can pull it outside of your integral, and you can work on this. So for example, if I have a 4 in front of my semicircle equation, I could pull the 4 outside, deal with the semicircle, and then multiply it by 4, and then get my final answer. If you have just a number, there's no variable, the formula becomes the constant times b minus a. And why is that true? This is explained simply by a picture. If you have y equals c, that's really a horizontal line. That's y equals c, right? And then you have your interval of a to b. So now you've drawn yourself a rectangle whose base is the difference, b minus a, and the height is c. So that's why this is a formula, c times b minus a. This is to remind you that you can add and subtract integrals like you did with indefinite integrals. This is definite integral because we have numbers here. Our indefinite integrals don't have numbers there, but you can still add and subtract integrals nevertheless. And then this other one is kind of interesting. This is saying that you can piece together integrals, because the integral now you are defined as area under the curve. So if I were to look at this and say, all right, take a pretend function f of x, and I have the first piece of a to c, right? That's my first piece, a to c. That's this piece right here. I want you to add it from c to b. This is my second piece, c to b. Notice I don't need the c in the middle. I'm really looking from a to b, and that's how you can rewrite it as one integral. Last one here says, if your function f of x is always greater than g of x, then the area under the curve will always be bigger. And again, hopefully that makes sense. You draw a picture for yourself and say that, all right, if I have f of x up here, this is f of x, and I have g of x down here, g of x. If I were to draw the same region from A to B, notice that my green area will always be bigger than my blue area right here, right? Because green is always on top of the blue, therefore the area is always bigger than the bottom one. Okay. All right, so in this next picture, next example here says express as one integral. It may be easier to see as a picture. You have your region, right? Here's your function, f of x. First one says from 2 to 7. So here's 2 to 7, this whole area. Then I want you to take away the piece from 5 to 7. So 5 to 7, I want you to take away this piece. So I'm only left with this piece. So rewriting this will be integral from 2 to 5, f of x dx. And that's it. You don't have a numerical value. You just have this answer. Okay? Last one, the main point of today is mean value theorem. You have two mean value theorems in calculus. You have the MVT for derivatives and you have MVT for definite integrals. This is the MVT for definite integrals. So the mean value theorem says that you're trying to find the average of your area under the curve, which is really hard to understand. So another way to look at it is to multiply this b minus a over to the left-hand side and have b minus a times f of x equals to this area under the curve. Okay, so far are you okay? If you're okay with the algebra, then the picture will make a lot more sense. What this is saying is you have a pretend function. Again, you have a pretend function f of x, and you are finding the area between a to b. Okay, we're saying that somewhere in this function, well, first of all, let's pause here. I now have this area, and this is defined by this integral, right? This is the area under the curve trapped between a and b. So calculus says, okay, there must be a C value in here somewhere, a C value, not necessarily exactly in the middle, but C value in here somewhere that I can go up and find the f of C value here and use that value to draw a rectangle that goes across A and B so that this rectangle that I just drew, the green rectangle, will have the same exact area as the red piece. Because this rectangle is this base, B minus A, times the height, which is f of C, right here. This base times this height, right? So it's saying that the two areas are going to be the same. Kind of an interesting notion, okay? All right, so, but in order to use the formula, we always need to bring it back to the first one, whereas the average form. So we just move the B minus A back into the formula here, okay? So that's also the average value. It's kind of a little bit hard to understand, but it'll make more sense once we start reviewing for the AP exam. So it says, find the average value and verify MVT for f of x equals x squared on the interval 0 to 3, given that the area equals 9. So the average value is equal to 1 over the interval b minus a times the area, which is 9. We don't need to do the integral yet. We don't know how to do the integral yet, okay? So 1/3 times 9 equals 3. That's the average value. At what value does the function take on its average value? So take your equation, f of c, which is c squared, and set that equal to your average value. So c equals square root of 3. We don't care about the negative root 3 because it's not in our interval. So what does this mean? This means that if I were to look at this, y equals x squared looks something like this. Between 0 to 3, that's my function, 0 to 3. That's the area I'm looking for. If I were to take my numbers and see that root 3 is right around here, if I put root 3 in and I use that to draw my rectangle, this green rectangle will have the same area as that weird triangular blue shape that I had with the x squared. Okay, and that's the value that will give me the same area, and that is your f of c. That's a c value you're looking for. Okay, that's it for the lesson.